me an introduction, come on.
So last our conversation will be given by Matt Berman, and he's going to tell us about the mechanics of shallow slip and upper plate deformation and tsunamigenic megathrust earthquakes.
So thanks everybody for hanging out. Today I'd like to talk to you about subduction zone earthquakes and the tsunamis they produce, which can often be much more destructive than the shaking effects. And I'm going to motivate this talk with some observations from the 2011 Japan earthquake, and then we're going to compare these observations to numerical models of a representative subduction system. And hopefully by the end I can convince you that the observations and models help us understand the earthquake rupture process and the tsunami that's generated. So for those of you who are unfamiliar, this is a quick primer on generating a tsunami. So during a subduction zone earthquake, the upper plate rebounds back towards the trench. This displaces the volume of water above it, and this propagates away from the source region. And when the wave gets close to the coast, it slows down. The water behind it piles up, and this wave crashes into the coast. Now it's important to note that if the earthquake is deep, there might be a lot of shaking, but the ground won't move very much under at the seafloor, and that won't produce a big tsunami. To get the big tsunami, the slip has to come all the way up near the trench and move the seafloor by a lot. And one of the biggest tsunamis in recent history happened in 2011, along with the magnitude 9 earthquake in Japan, and Japan was well prepared for a large event. They had built infrastructure to protect against tsunamis, like the seawall here, but the height of the tsunami exceeded their expectations. And as you can see, this had really devastating consequences. Now, one of the positive outcomes from this event is that we have this immense wealth of geophysical data to try and constrain the earthquake and the tsunami and why they happened, how they happened. So with that in mind, let's actually look at some analyses of the event. This is Japan. This is the subduction trench where the Pacific plate descends westward underneath the island of Honshu. And shown in the red colors here is a model of the slip that happened on the earthquake, showing the magnitude and location of slip. This is based on shaking recorded at seismic stations. And you can see this model puts the largest slip, about 40 meters, down about 100 kilometers from the trench. This puts it at about 35 kilometers depth. And there is some slip up near the trench, but it's less than down here. It's about 10 or 15 meters up the trench. And there have been some other seismological models, many seismological models of this earthquake, and most of them have a similar pattern to this, with large slip down here and some, but less slip up at the trench. The same analysis can be done using the tsunami data. And so if we trace back the amplitude and timing of the wave to the source region, we can determine the slip on the fault from the tsunami itself, which is compatible with 40 meters of slip up at the trench. So there's this inconsistency. Seismic data show large slip at depth and less slip up at the trench, but the tsunami was very large and showed large slip up near the trench and large slip at depth. So I want to try and answer the question, how does large slip occur up near the trench without producing much of a seismic signal? And in order to address this, we're going to actually look at the deformation that accumulates before the earthquake, because when this elastic strain is released, it drives the slip on the fault and it drives the displacements of the seafloor. So I've set up a very simple model of a subduction zone. It has a subducting plate shown in blue here that's dipping at 25 degrees. It's just a single plane, and it descends under a triangular upper plate. I put 1 meter of displacement at the top and the bottom of the subducting plate while I hold the back of the upper plate fixed. This is the relative motion. And now I need to decide what to actually put as our boundary conditions on the interface. So in order to build up elastic strain energy, we need to have part of the interface locked. And I've kind of represented it with this gray region here. I'm making the simplifying assumption in this model that anything outside this locked region is going to be totally free to slide with no resistance. But I do have to decide exactly what part of the fault I want to lock. So to do that, I'm going to look at the distribution of earthquakes in subduction zones. So this is showing histograms of earthquake depth in 3 different subduction zones, Sumatra, South America, and Japan. And where these earthquakes are happening is where the fault is stuck and occasionally popping off in earthquakes. So we can see there are very few events up shallower than about 15 or 20 kilometers, and there are very few events deeper than about 50 kilometers. I do want to note that Japan is a little bit unusual in that, for these 3 settings, in that it has more events in the 40 to 50 kilometer range. But I'm going to lock my fault between 20 and about 45 kilometers depth. So when I do that, I produce a distribution of slip on the interface. So just to orient you here, this is a picture looking perpendicularly down on the interface I showed you from the model. The bold black line is the trench for reference. So this side is at 0 depth. This side is at about 200 kilometers depth. And the colors here represent the amount of slip on the fault in my model. The dark colors are 0 slip, the light colors are the full 1 meter of slip. And this rectangle is the zone I've locked. By definition, it has 0 slip in it. Outside of it, even though these regions are free to slide, this part is actually holding them back. It's restricting them from the full motion. So you can see this area in red here is slipping 50 centimeters or less. Now we're really interested in what happens up dip of the locked zone between here and the trench, and you can see this is all dark red in here. Basically, no region in here slips more than 30 centimeters. So this is telling us that no matter what the frictional conditions are up here, this part can slip a lot during the earthquake. What this model doesn't tell us, though, is how that slip is going to happen, whether it's going to emit seismic waves or not. So let's take a little bit different view through this model. We're now going to look at a cross-section through the middle. Okay, so now we're in cross-section. You can see here's the subducting plate. We've got the upper plate as this triangle here. And remember, we're moving the top and the bottom of the subducting plate and holding the back of it fixed. The locked zone is right in here between these 2 red areas, and everywhere else on the interface is free to slide in this model. Okay, the background here, I'm plotting something called the effective stress. You can think of this as just the amount of deformation that occurred in the model. On top of that, these are the displacements that occur in this cross-section. And you can see the areas that are associated with high stresses are where the displacements are changing, where they're spatially varying. And this is an important point to keep in mind. We have high stresses where the displacements change magnitude or direction, but we can also have high displacements like down at the bottom of the subducting plate. They're not changing, there's no deformation in that region. Again, we're interested up here near the locked part of the interface and the trench, so let's zoom into that section. And again, we can see this part, which is locked, has the highest stresses, but there's this region up here that's up dip of the locked zone and above the unlocked part of the interface. And you can see it's blue. It doesn't have much deformation in it. But despite not having much deformation, these arrows are 60 or 70 centimeters long. So it's moving quite a bit, but it's moving it as a block along with the rest of the upper plate. It's not accumulating much deformation. So when we have an earthquake and we rupture the interface, all these arrows are going to switch directions and the upper plate is going to rebound back this direction. When that happens, the part here is going to release a lot of this elastic deformation. And that gets released, at least in part, as seismic waves. So if we have a seismometer measuring shaking, we can trace that back to this part of the fault right here. When this part moves up here, it's still going to move a lot. It's going to move, this 60 or 70% of the total motion, but it's not deformed, so it's not going to release any seismic energy. So this may account for why we get large displacements up here. They move the ocean floor and produce a big wave, but they don't produce much seismic radiation. Now, the question you want to ask is, okay, that accounts for maybe the slip model, but is this actually supported by observations? So we want to see if there's evidence for the 30 kilometers near the trench moving as a block instead of a deforming with strain release during the earthquake. So this is a complicated figure. Let me walk you through it. After the earthquake, a team of scientists went out in a boat near the trench and took measurements of the bathymetry in a place that they had measured the bathymetry before the earthquake as well. So here's the absolute bathymetry that they measured with the trench area shown right here. And what's really cool about this is now we can take the difference between the post-earthquake and pre-earthquake bathymetry. That's shown in C and D between the bathymetry taken in '99 and 2004. And then we can also compare that to the pre-earthquake difference. So if we zoom in on that, this is from 2004 to '99, the difference between those two tracks gives us a rough sense of the amount of noise in the data because the surface hasn't moved very much in 5 years. But then when we look at the earthquake difference, 2011 minus '99 track, we see that this entire region near the trench is shaded red. That means during the earthquake, this part moved 40 to 50 meters. But since it's all red, there's no variations in how it moved. It did, in fact, move as a block eastward during the earthquake. Now, if we go out to the west here, we can see the displacement start to decrease. That is indicative of strain release. So we can compare that to our models here, and I've just reversed it so we can think about this as the Pacific plate and the Japan up here. And so this area within 30 kilometers of the trench is like this one here. It's just exhibiting block motion. And then when we get farther from the trench, that's where we're getting the strain release. So this can account for why we don't see much seismic radiation coming from up here, but we can get a large tsunami that's produced. So with that, I'm going to just leave my conclusions up here, and I'd like to take any of your questions. Thank you. Yeah.
Could you go back one slide?
Yeah, sure.
So one thing I've noticed is right at the edge, right at the trench, there's a huge amount of motion. Is that significant at all?
They interpreted this as a slump or a landslide during the earthquake.
Okay.
Yeah. So it's not a part of this block motion here. It's actually something that happened right near the trench where it might have ruptured out to the surface.
Okay.
Yeah.
I recognize it's not part of your study, but is it surprising that nothing moved on the seafloor between 1999 and 2004? If this is like an area that might be like aseismically deforming?
So yeah. Certainly during this part, there's still loading going on, and we can actually look at plate motions to figure out how much motion that there should have been, and it should have been order 50 centimeters or so. And so we're looking at the changes in elevation. These are meters of in this case. I don't actually think this is elevation. I think this is horizontal motion. But the elevation changes up here are still meters compared to sub-meter levels down here. Yeah.
Where does your 1 meter come from? Like when you showed your model and like you had 1 meter at the edges.
Yeah.
Where does that come from?
So that's just, so these models are elastic models, and so we just choose 1 meter because then we can scale that to any value because it's linear elastic, and we can say, well, if it's 8 centimeters a year or something, then we can just have that multiplicative factor, and that will the deformation will scale with that. So it's just it makes it easier to do those. Yeah, Chuck.
Just a comment, I do the same thing with the slip. I use one shear modulus that's too high. One of the ways that you can boost the seismic energy coming out of that, I like your model, is to actually decrease the shear modulus up there, and that's the way Thorn, for example, gets booming displacements from the seismics up there. But they're not well constrained for other reasons.
Yeah.
I'm slightly confused. So, do you have 40 to 50 meters of slip along the fault, or is it vertical subsidence?
This is 40 to 50 meters of eastward motion of the surface. So when you're up here, that's very close to the amount of slip on the fault because the dip is very shallow here. So it would be it'd be a similar amount of slip on the fault up here.
How can you have that much slip on a fault and no seismic activity resulting from it?
Yeah, so that goes back to this part right here. Remember, we left this unlocked. It's not stuck at all, but it's accumulating a whole bunch of slip deficit just by being near the stuff that is locked. So during the earthquake, when this stuff slipped, it can still move a whole lot. It doesn't have to be stuck.
But how is there no seismic signal of that slip if we have rock moving on rock?
Yeah. Well, I mean, I think there is probably some seismic signal in the sense, I made the simplifying assumption that this is totally frictionless, but there probably is some, small friction value there that would play into that. But it's much less than the seismic signal you get from the locked part unlocking. Sorry. In back, yeah.
Do you have a hypothesis for why that particular segment would be locked? Is there some relief on the fault plane or some?
No, this is just, that kind of goes back to this picture here. It's where the earthquakes are popping off, and we see this in subduction zones all around the world. The earthquakes are constrained to depths of about 20 to 50 kilometers, so we sort of interpret that section as the part that can nucleate earthquakes.
But what's the actual physical process that's going to be?
Yeah, somebody call a rock mechanicist. So the idea there is you have some sort of velocity weakening friction. So when, if you're in between earthquakes, you're stuck. And then if you start slipping the fault, the friction will drop and the fault will sort of catastrophically fail. Chris?
So you pointed to that idea that the up-dip part had some accumulated slip deficit.
Yeah.
But I think some of the models up there could indicate that you could accumulate that big slip even without anything for a slip deficit. You have so much energy down below.
Certainly.
And you're rupturing up into a region that has such low normal stress,
Yeah.
such low strength, that you're just blasting through,
It's-
regardless of whether there's anything really locally accumulated there.
Yeah. It's actually really hard, though, to think of a sort of model in which the upper plate up here is sort of totally decoupled from this. So these sorts of models demonstrate that this part has to be accumulating slip deficit. And that may be, maybe it did have some overshoot with the dynamic rupture through there. That may account for why it's, 10 meters bigger up there than it is at the down dip part. But certainly it's very hard to imagine a scenario where this part is totally decoupled from what happens over here.
Thank you, Matt.
Yes.